All right, so let's get started for the day. This is going to be video 2 of 2 for day 1, and it's on the section 2.3 Techniques for Computing Limits. So we have a few limit laws that make life really easy. Someone else already did the work for us, and now we just get to benefit from that. And don't worry, after I introduce all of these, we're going to go ahead and do some examples to make sure that you guys really understand how to use these limit laws and whatnot. Hopefully my audio sounds a little bit better and there's not a whole lot of rustling going on because I got a new microphone. So it's supposed to be audio damping, so we'll be in a really good spot. So let's talk about this first slide, the sum and difference of limits. Our first thing is the sum of limits. So if I have two functions and I want to know the limit of the sum of those two functions, it's the exact same as knowing the limit of one function plus the limit of the other function. So let me go ahead and get out my spotlight little dude. So we can have the limit of the sum of two items is the same as the sum of the limit of each individual item. And because addition is just the opposite of subtraction, we know that the limit of the difference of two items is the same as the difference of the limits. So these slides are going to be posted. I intend to post the other slides from the previous lecture so that you guys have access to them and you can go ahead and reference these when you're doing your homeworks. So that's the sum and difference. Let's move on to a constant multiple. So sometimes you've got a number like 6 or 7 or 10 million multiplied out in front of a function that's being evaluated at some variable x, but that number really doesn't do anything for us. It doesn't tell us anything about what's going on. So as long as some value c is a constant value, as in it's one that does not depend on our variable x, we can go ahead and pull it outside of our limit. So the limit as x approaches a of some constant value c times a function is the same as c times the limit as x approaches a of our function f of x. I know this is all probably going to be coming pretty fast at you, but feel free to pause these videos. That's one of the reasons I uploaded them on YouTube, is so that you guys have plenty of time to write things down, really let it simmer, and go over my examples again and again. So if we have a sum and difference limit law, then we better have a product and quotient limit law. So for the product, the limit as x approaches a of a product of a function f of x and g of x is the same as the limit as x approaches a of f of x times the limit as x approaches a of g of x. So we can just separate those right off the bat, which is pretty convenient for us. And then if we have a product, then we better have a quotient. This should say quotient. My apologies. I'll fix it before I upload the slides. The limit as x approaches a of a function f of x divided by a function g of x is the same as the limit of x approaches a of f of x divided by the limit as x approaches a of a function g of x. And as long as the limit as x approaches a of g of x does not equal 0, we're totally in the clear and we don't have to worry about anything. And then finally, we've got power and root laws. So let n be a positive integer. That means it's going to be a whole number greater than 0. So 1, 2, 3, 5, 10, 100, all those sorts of numbers. And the limit as x approaches a of a function raised to a power n is the same as the limit as x approaches a of that function, whatever that value is, raised to the power n. And power is the same as we have quotients and products, and as we have sums and differences, we have powers and roots. So for the roots, if I have some function raised to the 1 over n power, then I can just say that the limit as x approaches a of f of x to the 1 over n power is the same as the limit as x approaches a of f of x, that value raised to the 1 over n power. And let's go ahead and do an example. So here we have a few limits already defined for us. We suppose that the limit of a function f of x as x approaches 2 equals 4, the limit of a function g of x as x approaches 2 equals 5, and the limit of a function h of x as x approaches 2 equals 8. And we can use our limit laws to compute the following. So the first one is the limit as x approaches 2 of quantity f of x minus g of x over h of x. Well, we can start from the outside and build inward, and the outside is going to be that that quotient rule. So we can use our quotient rule to write the limit as x approaches 2 of f of x minus g of x all over the limit as x approaches 2 of h of x. And then we get to use our difference law on top, and that's just going to be the limit of the difference is the difference of the limits. And so we get to write from the difference law, pardon my shorthand, from the difference law, we're going to have f of x, which is 4, minus g of x on top, divided by 8. And that's going to be -1 divided by 8. And that's our answer. And in the homework, there's a couple questions that ask you to do something just like this. And I do expect that you go ahead and write down because of the quotient law, because of the difference law, because of the product law, when you go ahead and take each next step. So let's move on to something that uses a few more. So right now, our biggest operator out here is a sum. So we have our sum law. We get to write we get to rewrite our first line just like that. And then the first one still has some things that we need to break apart, so we can go ahead and use our product rule and our constant multiple rule to break that apart. We get 6 times the limit of f of x times the limit of g of x plus the limit of h of x. And all of this is as x approaches 2. That leaves us with 6 times 4 times 5 plus 8, which is equal to 128. So let's go ahead and finish strong, and this time we're going to be using the power rule. So from the power rule, we get to pull that cubed term all the way out. We get to pull this cube term all the way out, and we are interested in the limit as x approaches 2 of g of x, whatever that value is, which happens to be 5, and we're going to raise that to the power 3, and our result is the value 125. All right, so now's a really good time to go ahead and take a pause, maybe take a deep breath, because we're going to jump back into the notes, but it's going to be a new topic. All right, so hopefully you took a pause and just a little deep breath and you're ready to start on a new idea. But this first idea is polynomials. And a polynomial takes the following form with a sub I as real numbers. So those are numbers that don't have any imaginary components to them. And any of them could possibly be 0. We don't really care about that. And x to the power j as powers of the variable x. So anytime that you have an equation that looks like the following, you know that it's a polynomial. So I have a sub n times x to the power n plus a sub n minus 1 times x to the power of n plus 1, a sub 1 x to the power 1 plus a sub 0 to the power x, or times x to the power 0. So this is a lot of information to sort of take in, and it might not seem very useful to you, but we're going to see some examples, and hopefully those will get you going in the right direction. But I've got a few notes for you. So based on our definition of what a polynomial is, we know that the equation for a line, y equals mx plus b, is equal to a polynomial. And why do we know that? We know that because anything x to the power 0 is equal to 1. So I could say 15 to the power 0. I could say negative a million to the power 0. And no matter what I do, I'm always going to get the value 1. And anytime you see a number x to the power 1, we know that that's just x. So our original form, y equals mx plus b, our a sub 1 is equal to m, x to the power 1 is equal to x, plus x to the power 0, which is just equals to 1, times b, which is going to be our a sub 0. So y equals mx plus b is certainly a polynomial. And when it comes to polynomials, well, we can just plug things in. So let p and q be polynomials, and let a be a constant value. Then the limit as x approaches a of a polynomial p of x equals just p evaluated at a. And we'll see what that looks like soon. And then when it comes to rational functions, so a polynomial divided by another polynomial, and as long as our polynomial on the bottom, q evaluated at a point a, does not equal 0, the limit as x approaches a of a polynomial p of x divided by a polynomial q of x is equal to p evaluated at a divided by q evaluated at a. So let's go ahead and let's see another example. So here we want to find the evaluation of the limit as x approaches a of a polynomial p of x, where p of x is defined as 7 times x to the power 3 plus 3 times x to the power 2 plus 4 times x to the power 1 plus 2 times the value 1. So here we can use our limit laws. That's certainly one way to do it, or we can just go ahead and plug in what we're doing, right? And here we're only concerned with a. So I'm going to go ahead and use our limit laws and spice things up real quick. So using our limit laws, using our sum limit law, I can go ahead and split up my polynomial into 4 distinct terms. And each one of these terms has a constant variable times it, or something like that. Or it's being raised to a power. So we can go ahead and simplify this a little bit more. So I've gone ahead and I've used my constant multiple and my power rule to pull out my 7, my 3, my 4, and to pull out the root or the power, because we really don't care about that to start with. The first thing we care about is what happens as x approaches a. And when x approaches a, we just get the value a. So we get and you might be wondering what's going on in this very last term. And the limit of 2 as x approaches a, well, it doesn't depend on x. So it just is always going to be 2. So that's why you see each step I take, it just becomes 2. But here we have the original limit as x approaches a of some polynomial function. We went ahead and we used our limit laws, and we ended up with just the polynomial evaluated at a point A. Now, hopefully that makes some sense to you. And if it doesn't, feel free to watch this video or shoot me an email and we can go through another example during office hours or something like that. So finally, let's work on example 3. And here we've already sort of proved our limit laws. So why don't we just use theorem 2.4 and the rational functions, limits of rational functions, to just plug and chug. So I'm going to just plug in my value 2. So after I plug in 2 anywhere I see an x and I evaluate, I end up just getting the value 1. And that's pretty neat, at least I think so. So we've worked through a couple of examples, and plugging and chugging has worked for us so far. So at least based on the homework, that's going to be a good way for you to go. So feel free to go ahead and start on the homework, and I look forward to seeing you. Oh, let's actually talk about the homework. So the very first homework problem. So I said in our syllabus meeting that the homeworks would be online, and it turns out that right now we actually can't do that. So let us talk about homework number 1. Homework number 1 is going to be a written homework. And here we've got that there's 20 points possible. So you can earn a maximum of 20 points. You can earn a minimum of 0 points if you just choose not to turn anything in. I highly recommend choosing to turn things in because, well, it's worth 25% of your grade. But hopefully, based on the examples that I've done in the notes and based on the lecture videos, you'll be able to figure out exactly what we're doing. So the first section is a 7-question true or false section. So just if f of a exists, then our limit as x approaches a of f of x equals f of a. It's up to you to decide whether or not that's true or if it's a false statement. If it's false, you don't have to give me a reason why, just state that it's false. I've got a couple touchy-feely questions right here in the middle. I feel confident in finding limits using graphs. I feel confident in finding limits using tables. I feel confident emailing my instructor if I have trouble understanding or accessing materials. True, false, I just kind of want to get a little bit of feedback on this first homework. I've already gotten emails from a couple of you, and I really appreciate the boldness, just you guys feeling comfortable reaching out to me, and hopefully I'm going to respond to all of them, or I'll make a video that encompasses all of the answers. So we've got a true or false section, and then I've got one short question. So question number 1, in your own words, explain what the limit as x approaches a of a function f of x equals L means to you. And you can feel free to use sentences or draw a diagram or come up with some interpretive dance, whatever makes sense to you and whatever is an easiest way for you to convey meaning to me, that's what I want you to do. So feel comfortable doing anything. And then just like in examples, I've got using graphs to find limits. I've got a couple questions like that, using tables to find limits. And you might say, Emily, I don't want to do a million of these, but the easiest way to learn this sort of stuff is just to do it over and over and over again until you can't get it wrong. And then we've got right-hand and left-hand limits using a graph. We've got polynomials. We've got rational functions. And then problem number 11 is kind of expert mode. So I understand if problem 11 doesn't go that well, that's okay, because we've got the limit as x approaches 5 of a function. 4 times x squared, well, 5 squared is 25 times 4 is 100, so I've got a 0 on top. 5 minus 5 is a 0 on the bottom. I've got 0 divided by 0. What am I going to do there? So I definitely want you guys to use the right hand, left hand limit to show me, well, what happens near 5 and see what exactly you come up with. So this one's going to be a written homework, and hopefully you'll just maybe print out this page, fill it in, or fill it in on a piece of notebook paper, scan it using a camera on your phone or a scanner or anything like that, and upload it. And I'll be able to accept it as a written submission, and I'll be able to grade it right then and there. All right, that's going to be it for today. Email me if you have any questions.